Good morning, everybody. Welcome to Educational Round 91. I'm going to be competing here and then showing my solutions. At the end of the video, I'll have solution discussions for like all of the problems that I end up solving. If I only solve like some of them, then I'll only talk about those problems, or at least the ones I know, or I think I know how to do. But we'll see. Vuv is back as a writer, or Vovu maybe. Don't know how to pronounce his name. The king returns. So good luck, have fun. Hope you enjoy the contest as much as I will. I guess we'll see how much I enjoy it. Timers are a bit off. Ready, go. Oh, alright, let's try some of these alternate sites. Come on, Mike, you can do it. Oh, here we go. I'm gonna open all of them. There we go. Okay, we got the problems. Good. You're given a permutation. Recall that the sequence of n integers is called a permutation if it contains the integers 1 through n exactly once. Good. Find 3 indices such that they are increasing and it increases then decreases. Or say there are no such indices. Yeah, so we just find, this should be easy to do, I guess. Alright, so n equals this. So we'll take in our array, and then yeah, okay. So if a at I is less than start and mid equals -1, then we can reset our start to be this. Just a and start rather. Okay, so now otherwise, if a at I is greater than a at start and mid equals -1, then we can set our mid to be equal to I. Otherwise, if a at I is less than a at mid, yeah, that should be the only, well, mid shouldn't be -1 here. Otherwise, so if it's less, then we have our answer, and sys out start plus 1 plus a space plus mid plus 1 plus space plus I plus 1. Otherwise, then we want to just set mid to be equal to I. Oh, and then what do? We print no. So I think this should be fine. It's just a greedy. Yes. Hello. 2, 3, 4. Oh. Yes, 2, 3, 4. Yes. 1, 3, 2. Oh, 1, 3, 2. Yeah, that works. 1, 2, 3, rather. And then no. Okay, let's submit. If Code Forces is down, I don't know if CF notifications is going to work. I hope I'm not the one causing the performance issues by publishing that tool. I'd like to move on from this. Maybe I'll read B and check back every so often. That's A. Recently, you found a bot to play rock, paper, scissors with. Unfortunately, the bot uses quite a simple algorithm to play. It has some string of length n where each letter is a rock, paper, or scissors. When initializing, the bot is choosing a starting index, and then it can play any number of rounds. In the first round, it chooses rock, paper, or scissors based on the value of this. Okay, yeah. The second round, whose choice is equal to the next character in the string, and the third round of the next one, and so on. After n, it returns to the first character and continues the game. Come on. Come on. Well, it seems unlikely this is rated, but oh well. Okay. You plan to play n rounds and you've already figured out the string s, but don't know what the starting index position is. Since the bot's tactic is so boring, you've decided to find n choices to each round to maximize the average number of wins. Find n choices. Decided. Wait, you're going to play n rounds. Okay. You decided to find n choices each round to maximize the average number of wins. In other words, let's suggest your choices are these things. And the bot starts at this position. Do you have to choose your things ahead of time? Oh, I guess you do. Well, you always want to play the same thing, don't you? Like, why wouldn't you? Yeah, okay. I think this is just a boring problem. Because, like, I don't have a proof for it, but like if you're going to start at every position, then the chance that each one of your positions affects each one of their own positions. Oh, do we submit? Ah, come on, Mike. Let me submit, Mike. Anyway, yeah, so we'll just keep coding. So the idea is that each one of your moves could be equally likely to play each one of his moves. So you just want to play all the same thing. Yeah, rock, paper, scissors. So what beats rock? Paper beats rock. Paper is beaten by scissors. Scissors is beaten by rock. Okay. So now int array count equals new int 3 for their C1 line. Counts at RPS dot index of C++. And now max stack is equal to 0. Now we know the index of the most common thing. And we come up with a string of n characters. I guess the same length always. So for int I equals 0 as less than line dot length I plus plus. We print beat dot caret max stacks and then a new line. If I'm understanding the problem right. Yeah. Okay. Can we submit? All set a timer for like 5 minutes and then come back when the timer goes off. How about that? Yeah, okay. Create the teams. There are n programs that you want to split into several non-empty teams. The skill of the ith programmer is AI. You want to assemble the maximum number of teams for them. Yeah, okay, I understand, I think. There's a restriction for each team. The number of programmers on the team multiplied by the minimum skill must be at least X. Each programmer should belong to at most one team. Some programmers may be left without a team. Calculate the maximum number of teams you can assemble. Surely Gritty works, and we can just sort them, right? So 2, 5, what does the minimum have to be? It's gotta be 10. Oh wait, can you not use some people? Maybe you cannot use some people. Yeah, you can choose not to use people, I see. So you can do 5, 7, and then 9, 11. Yikes. So then greedy still works, but we just go from the other side. So it would be 11, then 9 and 7. Yeah, okay. Very good. And n equals this thing. How big can this be? Max equals, or I guess this is, we'll just call this k. Cool, so we have our, they don't have a bound on the sum of n. That means there could be 10 to the 8th input. Uh-oh. Uh-oh. Okay, there won't be. I trust they're not evil. But I also have no confidence that this round won't be unrated. But that's fine. Because it wasn't rated for me anyway. Yeah, okay, so well. So we're gonna go from the right end to the left end, and now long product is equal to 1. So while the product is less than or equal to k, how big is k? K can be 1. So this is not gonna work. Let's say while the product is less than or equal to, or started at AI. Now when it's less than or equal to k, less than k, then length equals 1. So really we want well, the length times a at I minus length. So many mistakes. The length times the long of a at I minus length plus 1. Well, this is less than k. Then length plus plus. Okay, we also need and length minus 1 less than or equal to I. We don't want it to be out of bounds. So while this is the case, increment length. Okay, so now if length minus 1 is less than or equal to I, that means we found a legal way of doing it. So we can make our new group, and we also want to move I over. And then we don't want a TLE here, so now else I equals this one. I think that should be fine. So it does this wrong for some reason. Why would that be? Length times a at, this should be n minus 1 minus 1 plus 1, so n minus 1 is less than k, so that should be false. So we should take 11 I minus equals length minus 1. I don't know where I got that from. Oops. Try to resubmit. That was that timer. No. All right. Let's set another 5-minute timer then. Okay. So it is kind of fun though to just be living on the edge in this sense, like just not know whether we're right or not. So I think this is the right approach. Let's double check for overflow. We cast to longs here, that should be fine. Everywhere else should be fine. This should take care of our TLE issue, and then this should be order n after the sort. So we should be fine. Okay, Berserk and Fireball. There are n warriors in a row. The power of the ith warrior is AI. All powers are pairwise distinct. You have 2 types of spells which you may cast. Fireball X. You spend X mana and destroy exactly K consecutive warriors. Or Berserk, you spend Y mana. Choose 2 consecutive warriors, and the warrior with the greater power destroys another chosen warrior. Oh, you like control them. Got it. Consecutive power. The warrior with the greater power destroys another chosen warrior. Any other chosen warrior? Or the other one that you chose? You cast Berserk on warriors 8 and 11. The resulting sequence becomes... Okay, so it destroys the other one. So this should be the other, not another. I see. Then, for example, if you cast Fireball on consecutive warriors with powers 7, 11, and 5. Oh, okay, so it goes through the... Got it. You can, or you want to turn the current sequence of warriors. Oh, you have to change them. So it's 5, you want it to be 2. What is this thing? Oh wait, this is 5 and 2. And these are cost of Fireball, the range of Fireball, and the cost of Berserk. You have to choose exactly K warriors. What if it's impossible? Oh man, this is kind of annoying. Is it a permutation? Oh, they are distinct. Okay. So they're just like... They're just like people you have to destroy. So it's like destroy all of these people, pretty much. So if there are ever fewer than K in a row, then we can't use Fireball on that range. And also, I guess all of these are independent problems. If we can't ever destroy the people that we like, then like that's just an infinite barrier. We can't get around that. So, oh, we could use them to destroy other people, I guess. But you could treat them as independent problems still. Since they're all independent, you can always use Berserk to destroy one person in the range. Unless it's one guy who's bigger than both of you. So, man, this is kind of caseworky, but I think I should be able to handle it. So there are a couple cases. So if it's less than, if the size is less than K, then let's try to submit again. Set another timer. Okay. Yeah. Where was I? I was over here. So if it's less than K, then we have to destroy them with only Berserk. Which means that the max in the range needs to be less than the max of our two endpoints. Okay, so if it's not less than K, then we have to use K a couple times. And then after that, we could either use Fireball a bunch or use Berserk several times. So maybe we brute force the number of Berserks. And then we care about the max of the two endpoints. And also the max in the range also matters. And I think as long as we're just like careful with this implementation, we should be fine. One test case, somewhat nice. Length of the sequence, A, the length of B, respectively. Man, I really hope this isn't my fault. I really hope it's not a bunch of people are using CF notifications and that's taking the website down, because that would be unfortunate. And the worst part about it is that the best solution to this problem is to use CF notifications once you submit, because after you've submitted, CF notifications will tell you what the result is, even if the servers are like dying. So like the solution most people would want to use to this problem is also, or might be, I don't know, probably not. Probably aren't that many people using it, but it might be a cause of the problem. Okay, so int n is this, int and keep this, fire cost. Okay, so we have the cost of everything. Now what do we need? The original array. Oh, they are just all distinct? Oh, yeah, so it's a permutation then. Okay, int array keep, well, okay, so we'll set each of these things to true. Now we need to go through and process our array. So if, oh, we also have this prefix and suffix thing that we need to destroy. Yeah, okay, so let's do this. So static, let's try again. No. Code force is just like permanently done for. Oh, I shouldn't, well, I guess I don't need A anymore. That's unfortunate. Okay. How about I set a timer for, let's do like 15 minutes. We'll check again in 15 minutes. Because I don't think at this point, penalty is not really, I'm not too concerned. I just want to solve problems because they're fun. So static long, or static, I guess, yeah, static long in cost, array list integer middle, int L and R. Okay, so now we need to make a bunch of things static. Static int fireball cost, fireball range, berserk cost. I guess that's it. Can keep be 0. Keep is at least 1, so that's fine. So, okay, boolean possible is true, long cost was 0. 4 and die equals 0, as this thing x plus. If keep at term at I, then we can process this prefix. Okay, so this means this is like the first guy we care about. So then long res equals min cost. Oh, we should make an array list here too. Add term at I. So we either add this to the list of things we need to destroy, or we process it. Process the prefix. The left will be -1, the right will be term at I. Okay, res equals -1, and possible equals false, otherwise cost plus equals res. We'll do the same thing with the suffix. I equals n-1, greater than or equal to 0, minus minus. This order doesn't matter, but I think it will be easier if I need to debug things. And then do that. Okay, awesome. Good. So we should also make the first index equals -1, last index equals -1. First index equals I, last index equals I. So if it's not possible, let's return right away. otherwise for int I equals first index, true, all right, that's this. So we're going to go from this first index, we need to find the next thing. So for int next equals I plus 1. Well, next is less than last index. And, oh, I guess if first is not equal to the last. If there's only one person we need to keep, then we'll just handle the prefixes and suffixes. This is more caseworky than I wanted it to be. I guess there's certainly a better way of doing this, but okay, well then this is fine. So now well not keep at perm at next plus plus. So now we have these two things we want to handle. Oh, we can just do this. So well I is not equal to last index. And now here we'll just say I equals next. Good. Okay, so now we just need to handle it. So we can do prefix clear here. And then when we increment this, then we need to do prefix.add perm at next. And then here we can just process it. So we process this range from the first thing to the last thing. If it's negative 1, we print impossible. Otherwise we add to our cost, and then we reassign this. Okay, so now the only thing we have left is how to actually process some range. Okay, so if, well, int kill is equal to middle dot size. So if this is less than fireball range, then we can only use berserk. Maybe we just need to brute force berserk anyway. Should we just do that? That might just be easier. So long best equals max value. It's max value -1, otherwise just return best. Should have just used max value as a sentinel, but this is fine. So now, otherwise, we need to brute force how many people we're going to berserk. That might wind up being helpful, I'm not sure yet. So now for int to use, okay, so now if to use, or if middle that size minus to use, if this number is not divisible by fireball range, then this isn't going to be possible, so then we can just skip it. Okay, otherwise, if to use is equal to middle that size, then this might not be possible either, depending on L and R. So if middle, well, okay, if middle is empty, then we can just return 0 right away. So now we know middle isn't empty. So if we're trying to berserk everyone, we can win by only if max is bigger than middle dot get middle dot size minus 1. If we're bigger than the last one, then we could kill everyone if we wanted to. So best equals math.min best and berserk cost times, this is a long, right? Let's make it a long. Berserk cost times times middle dot size. Let's continue. Okay. If so now we know it's not equal to the middle size, and it is divisible by the fireball, which means we could definitely use it if we wanted to. There's no reason we couldn't, because we could always just use the people in the middle to kill each other. And now we do it with fireballs. We win with fireballs. And best equals math.min best and berserk cost times 2 use plus fireball cost times some stuff divided by fireball range. Okay, what is this stuff? This stuff is going to be middle dot size minus 2 use. I think that handles all the cases. It's wrong though. Array index out of bounds. Okay, so well, don't keep perm and next. Am I subtracting from perm? I am. What is this index? Index 5. How big is keep? It's n big. Oh, it's down here. So it can be this issue. Keep 3 and keep 5. At 0, next 1, next 2, 4 to 5. What is last index? First index is 0, 1, 2, 3. Oh man, yeah, we don't want I++. That's unhelpful. Cost is 8, that seems right. Cost is 0. That shouldn't be right. Oh man. The order matters. The order matters. That's silly. Nothing can ever move, right? Yeah, okay, fine. Fine. I will handle it. index of the parameter I is I. Okay, so int last index of equals -1. Int next thing equals this -1. Okay, so int next index equals index of the next thing. And if next index is less than last index of, then sys out -1 and return. Otherwise, last index of is next index. So Codeforce is back alive. Oh, there we go. Hoorah. Unexpected error. Are you serious? Can I submit to B? Okay, let's see if we can get D now. Alright, so we got A, B, and C. I love these submit times, they're hilarious. Okay, I think we're fine here. This is now -1. This is now 8. Good. This is now 0. Good. Now we just need to get rid of all the print statements. Oh no. Oh, also wrong answer. It's very unfortunate. It's very unfortunate indeed. I'm misreading the problem. Exactly K. Choose 2 consecutive warriors. The warrior with the greater strength destroys another chosen warrior. Yeah, okay. Last index of so these are all distinct. the index of ever decreases, then it's impossible. Is there any other time we wouldn't be able to make it? No, because it's just taking a subsequence, so that should be fine. So now the cost is 0. It's equal to -1, we set possible to false. If it's equal to -1, we set possible to false. We go through each integer. If we keep this and process the prefix, okay, then we clear the prefix before looking at this, and then we clear the prefix each time here. So we can use berserk from 0 to this many times. Berserk cost times to use, fireball cost times, oh shoot. Yeah, this is a problem. That's gotta be this. That's important. Yeah, that's that matters. That would do it. Let's look for all my multiplications though. That should be a long, I think. That's a long, we just decided. This should be a long. Good, okay. So yeah, if you multiply before, like, I wasn't flooring in the right place. Oh no. Interesting. What do we do? Do we move on, or do we keep banging our head against this? I guess we keep banging our head. How many wrong answers do people have? A couple. Oh, the fireball range. Wait. Yeah, that's fine. Do they have to be adjacent? Consecutive warriors. If it's not equal to the middle, you can always destroy. You can always destroy as many people as you want. You just have the bigger person fight someone either on their right or on their left. If it's equal to the middle, we're going to have to destroy the biggest person. I'm sorting the middle. How is this wrong? How is this wrong? It's kind of surprising that it's still rated. Wouldn't expect that. Because like the penalty is like massively. Like if you got your A submission in, you just have 30 fewer penalty points than everybody else. There they go. Fireball cost can be 1. Or fireball range. So cost plus equals res here. It's not impossible. Cost plus equals res here. Cost plus equals res. They are all independent. Why would this be wrong? It's not easy to write a brute force for either. To use is less than middle that size. equal to the middle of that size. So destroy up to all of them using Berserk. How is this not right? I don't know. I think I'm going to have to move on. Unfortunately. You have a set of n disks. The ith disk has radius I. Initially, these disks are split among m towers. Each tower contains at least one disk. This sounds like Hanoi. And the disks in each tower are sorted in descending order of the radii from bottom to top. You'd like to assemble one tower containing all these disks. To do so, you may choose two different towers I and j, such that each contains at least one disk. Take several, possibly all disks off the top of tower I, put them onto the top of tower j in the same order, as long as the disks on top of tower j are bigger than the disks you move. You may perform this operation as many times as you'd like. So it's like Hanoi, but you're smart. Okay. So there are only two possible operations. You can move the 1 to the 3. You can move the 1 and 2 to the 3. I see. Let the difficulty of some set of towers be the minimum number of operations required to assemble one tower containing all disks. For example, the difficulty of this is 2. Yes. You were given this many queries. Each query is noted by two numbers, this and this, meaning merge these two towers. That is, take all disks from this, blah, blah, blah. The resulting tower gets index AI. So merge B into AI. But you can do it in either order. For each K, calculate the difficulty. What is K? So like calculate how many things you would have to do if you do just these towers. Small to big, question mark? Sounds exactly like small to big. Man, why didn't I look at this problem earlier? Okay. Well, do I understand the problem? I don't know if I do understand the problem. N and M, the number of disks the size of the towers. Are all disks unique sizes? Looks like they are. Maybe, but what is this? There are 7 disks and 4 towers. So here are the 4 towers, maybe? The next line contains n integers, where T is the index of the tower that disk I belongs to. The index of the tower. So which tower? So this is in tower 1, this is in tower 2, this is in tower 3, tower 3, tower 1, tower 4, tower 3. Okay? Now we have all of our queries. Oh, I see. So they're like, here are all your disks, they're all unique. Here are which towers that they are in. Merge 1 into 3, merge 3 into 2, merge 4 into 2. So let's look at this. We've got 1, 2, 3, 4. So this has 1, 2, 3, 4, 5, 6, 3, 7. So 1, 5, 2, 7, 4, 3, and 6. All right, my understanding matches that. Now, what is the first query? Merge 3 and 1. So it's just how many parts does this get split into? So when we merge them together, we'll have 1, 3, 4, 5, 7, right? Yeah, 1, 3, 4, 5, 7. And when we have that, this is a change, this is a change, and this is a change. So that takes 1, 2, it takes 3 moves, right? Why does that take 5 moves? One, 5, 3, 4, 7. They're telling me this takes 5 moves? Oh, I see. They're like, yeah, they're not saying after you do it. They're saying if you do it optimally. Got it, got it, got it. Alright, so initially you have 1 split from 1, 2 split from 2, 3 split, or no split from 3. So you have 3 and 4 together. Yeah, so 3 and 4 are together. That's your new state. Then after you do this first query, the difficulty has decreased by 1 because we now have 3, 4, 5 together. After this query, what do we have? We have 1, 2, 3, 4, 5, and then we have 2 splits. So the answer is 2, yeah, it's 7. Okay, so this is small to big, and it's tree set maintenance. So when we combine 2 things, we have a bunch of, yeah, okay, so this should be very easy. D should also be very easy. I don't know, I'm getting D wrong. But we'll come back to that, I guess. N equals this, and towers equals this. Okay, so now the question is, well, we have a bunch of tree sets. Okay, so they're all non-null now. So now we're entitled to 0 plus. We want to tower is this -1. Towers at tower dot add I. And potential is going to be equal to n-1. So potential if tower contains I-1 and potential minus. So let's just make sure we've got that working right. Should be 5, that's right, okay. So for int I equal, or int q equals 0, q is less than n towers. Start at 1 really. Okay, so now we have some queries. In T1 is this, T2 equals this. So if the first one's smaller than the second one, this is going to be equal to towers at T1. Otherwise, it's going to be equal to towers at T2. We also will have this bigger one. The smaller is this one. This should be the second one. Otherwise, it should be towers at T1. Okay, then after we're done with this, then we want towers at T1 is equal to bigger. So now we just have to merge the smaller into the bigger. If yeah, so if smaller dot contains I plus 1, then potential plus plus, because we're separating two, so that will increase the potential. And okay, then we will remove it. So now bigger dot add I. And now if bigger dot contains I minus 1, then potential minus minus. If it contains I plus 1, then potential minus minus again. Five, 4, 2, 0. Good. So that is n log squared. Probably need print writer. This needs to be print writer as well. Geothermal's got G. Nice job from him. Are you kidding me, man? How do we improve this? We could use hash sets. This is like 100% intended. Do I convert to C++ maybe? Because the time limit is too tight? That might be the play. I could get rid of these additions. I could speed these up with array lists and then build it a little bit faster. That's unfortunate. I guess I'll try that. Yeah. Well, that shouldn't... I'm only doing a linear number of additions here, but I'm doing n log n additions here. Is there a better way of doing this than adding to a tree set? I need... Guess I could use a hash set. Yeah, okay, fine, hash set. Okay, add it. Okay, smaller Kansas, but now we need to add them in a small, from like small to big. So int array smaller values equals int array smaller dot size or int smaller. Okay, then sort these. Okay, so now for int I equals 0, I is less than smaller values dot length is plus. If I is less than smaller values, length minus 1, and for less than this thing, and also smaller values at I plus 1 equals smaller values at I plus 1, then potential plus plus. If this doesn't work, I convert to C++.
Well done, sir. AC on property.
Now what's the time limit there? Ah, man, it's just ridiculous. Okay. Fine. So, yeah, it looks like D I just need to get... Let's read these maybe, so we got lots of time. Actually, I gotta hang on. I'm gonna have to. I've got a team meeting that's supposed to be at 1, but now the round's late, so I'm gonna message my team and ask if we can push it back. Okay. So what am I doing? I'm reading problem F. Strange addition. Let a and b be some non-negative integers. Let's define strange addition of a and b as following. Write down the numbers one under another and align them using their least significant digit. Add them up by their digit and concatenate their respective sums together. Oh, 6. Yeah, that makes sense. Okay. You're given a string C consisting of n digits 0 through 9. You're also given n updates of the form replace this digit with digit D. Note that C might have leading zeros at any point of time. After each update, print the number of pairs A, B, such that these are both non-negative integers, and this is the result. The result of strange addition of A and B is equal to C. You have some string with some digits. You also have a bunch of updates that are updated. Now the question is, how many pairs of numbers can you add together to make equal to this? So like for all ways of splitting it up, well, I guess ones are special. Perhaps zeros are special as well. Ones and zeros are like the two special cases. Maybe zeros aren't special. Like if this C has no ones in it, then there's only one way of splitting it up. Because if you add two numbers, if it's going to be 2 digits, the first digit is going to be a 1. Like the biggest 2 you can add is 9 and 9. That's 18. And if the first digit is a 0, then you wouldn't even print the first digit. So anytime there's a 0, 0 has to be the second digit. And anytime there's anything, well really anytime there's anything that isn't a 1, it has to be the second digit of, like it's got to be the ones digit, it can't be the tens digit. Only ones can be the tens digit. Ones can also be the zeros digit. seems almost all easy to handle. There's not knowing how you split it up is the hard part to handle, I think. Like, what if you have a bunch of ones? Like, if you have 3 ones, how many ways are there of doing that? I think that's the interesting part. But maybe we can just handle that with the segment tree. Let's look at it. So if you have 3 ones, then you could do that. Well, your first, so you can take yeah, so the question is like how many ways are there of doing 3 ones then? You can do dp of I minus 1, and there's 2 ways to sum up to 1. You can do 0, 1 or 1, 0. You can also do dp of I minus 2, and that will be a sum of 11. How many ways are there to sum up to 11? You can do 1, no, you can't do 1. 1 and 9 doesn't work. You can do 2, 3, 4, 5, 6, 7, 8, 9. 2, 3, 4, 5, 6, 7, 8, 9. That's 8. 8. I can count. I'm good at counting. Solving a counting problem right now. I don't need to use my fingers to count because I don't have this many fingers. All right, so then there are 8 ways. And then, oh, I guess you're just the product of your kids, huh? Yeah, this is a cool problem. I might solve this problem instead of the obnoxious problem that I think I already have the solution to. Man, maybe I should just solve, well, should I? I spent like so long looking at it and I don't know what's wrong. We can do this with a treep. This can be done with a treep. I don't know if a treep is overkill. It's possible it is. Yeah, I have a very clear idea on how I would implement this with a treep. Let's maybe let's read Circular Dungeon. You're creating a level for a video game. The level consists of n rooms placed in a circle. The rooms are numbered 1 to n. Each room contains exactly 1 exit. Completing the ith room allows you to go to the next room. And completing the nth room lets you go to the first room. So it's a circular room. You're given the description of n chests. The ith chest has a treasure value ci. Each chest can be one of 2 types, regular or mini. Okay, regular, you just get it. Oh, mimic, sorry. Oh, so if you eat a mimic chest, you die. Good to know. The player starts in a random room, with each room having an equal probability of being chosen. The player's earnings is equal to the total value of the treasure chest he'd collected before he lost. For each k from 1 to n, place the chest in such a way that each room contains exactly 1 chest. Exactly k are mimics. The expected value of the player's earnings is minimum possible. You just want to equally space them? Yeah, surely you just want to equally space them. because like if you start on a mimic, wait, you just take the thing from every room, right? Oh, they have different values. I thought they all had value 1. Interesting. Okay, well, I guess that's not the problem for me to do because I've got 2 problems on my plate already. One of which I know how to do, but haven't started typing. The other of which I swear I have the right answer to. Okay, let's what's the plan? I guess spend 20 minutes on D, and then regardless of whether we get it, go to F and just code up F at the end. You have N warriors in a row. The power of the ith warrior is AI. All powers are distinct. Yes, we know. So you can destroy exactly K consecutive warriors for X mana. Or you can choose 2 consecutive warriors and destroy the smaller one. Everyone's power is distinct. Fireball cost, fireball range, berserk cost. Then I read in this permutation, make it all 0 indexed. Get the index of each thing in the permutation.
Always a pleasure hearing you work, sir. Understood, sir.
So this is the last index of all of the things that we care about. What things should we keep? Okay, so now this is the next thing. We should keep it. It's guaranteed to be distinct, so that shouldn't be a problem. Next index is the index of this thing. Am I using a print writer anywhere? I'm not. Print -1 and return. So if they go backwards in the array, if any 2 things switch positions, then it's impossible. Okay. So, by default it's possible. If possible ever gets set to false, then we print -1 and return. First index equals -1, last index equals -1. So this will set our first index. This will set our last index. Those need to be set because we have set something equal to be kept, because this end keep is at least 1. If we keep this thing, then the result is the minimum cost of doing this prefix, where we can't use the left side. Well, let's test this. So maybe we have 2 things. We want to keep one of them. Wait, what is this? What is the input format here? The cost of fireball is 10. The range of fireball will be 2. The cost of berserk is 1. So initially we have 1, 2. We want to keep the 2. So this should be possible in 1 move. But if we make this, we want to keep the 1, then it should be impossible. We make it 2, 1. We want to keep the 1. It's also impossible. If we make it 2, 3, 1, we want to keep it 2 and 3, then this should be possible in 1. Now it should be possible in 10. Looks fine to me. If we keep this thing, result is this min cost. Cost plus equals this result. Set our first index to this position and then break. Otherwise, add this to our prefix. And minus 1, I is greater than or equal to 0. I minus minus. If we keep this thing, so last index, if we keep this thing, this is the result. This is negative 1. It's impossible. Add this to our cost. Oh, damn it. So much time. Okay. Let's do this other problem now.
Well done, sir. AC on problem D.
Geothermal. Well done, sir. Nice win. Good job. Although, you know, it's kind of silly with what happened, but still, nice job. Nice job. Let's solve F now. Okay, so we for each, so the answer is just going to be the product of everything Yeah, the product, we want the product of, like, we'll split it into groups. And then each group will be a prefix of 1s followed by some number, maybe a 6. So if that's our thing, this is our group. So we need to calculate the number of ways of doing this very quickly. So we can have a DP of like x1s. And then the answer will be like ways of 16 plus DP of like 1s minus 1 plus ways of 6 times, so this should be times TP of 1s. That's how many ways you do this. All of them are now independent. Yeah, okay. Bring out the treep. Do we need a treep? Do we want a treep? I think we want a treep. Why do we want a treep? We want a treep because then we can merge things together because they're the same. Yes, that's why we want a treep. Okay. Give me my random. So now this is going to get a little bit messy. What do we need here? What did I write we need? Okay, lower priority on top, yes. To add seg tree supported methods, to lazy prop. We don't need any lazy prop. We don't need lazy prop. We can skip propagate and range add. Okay, we also get to skip all of these propagate calls, which is nice. Should be some nice constant factor stuff. Okay, so now split after this many things. So the issue is the size can now be kind of wonky. Yeah, okay. So things get weird here. So int n1s, and then also final value is what we need. It's a bunch of 1s, then a last value. All right. If you only need merging, skip, add, and rebalance. I think we only do need merging. We also skip rebalance. So small. Look at how it's amazing. I love it. Even with the giant font size. I guess it might be hard to read. Okay, so we need to recalculate now. So we also probably want a long anyways. That's what we need to calculate. Subtree size, we don't need the sum, we don't need to prop. Okay. Good, good. So now in this recalculate, subtree size equals this, or me dot n1s plus me dot, or plus 1 for the final value. Yeah, this n1s does not include the final value. Okay. So, Good. So now we should probably make this DP. Well, let's just make a method here and make it in the bottom. So static int go with ones, int n1s. If n1s is less than 0, return 0. If n1s equals 0, return 1. If dp if ones at ones not equal to 1, and dp with ones and ones. Okay, so now long ways equals, what can we do? Static int ways to make int value. So ways equals ways to make, we also need our math methods. Static int add, long a, long b. Do we need power or division? No, just subtraction though. A minus b mod plus mod mod. Okay, so let's make the mod now. All right, so we've got our mod. We can add, subtract, and multiply. So long ways would be multiply the ways to make 11 by go with ones and ones minus 2. We can make 11 here. Ways equals add ways to make 1. Go with ones. And 1 minus 1. Turn dp with ones and ones is equal to ways. Ways equals ways plus ways to make 1. This should be multiply. Yeah, so you can either do 11 with 2 fewer ones, oops, or you can make, what did I do? Make 11 with 2 fewer ones, or you can make a 1 with 1 fewer 1. Got it? So now what do we do? Ways to make. If ways to make a value is not equal to -1, and ways to make a value. For if first equals 0, first less than 9, first plus. Be less than or equal to, because 9s are allowed. Ways not 0. Oh, we can just pre-comp this. Ways to make at first plus second is plus. So let's pre-comp in the beginning, and then we need these arrays. Okay, so static int array ways to make, so int array something big. Static int array, what was this called? Go with ones, or dp with ones, so int array Okay. This should be ways to make at 11. Oh, this needs to be a long array. Okay, very good. For pre-comping, okay. So now I think we just need to do this. We also need to, I guess, modify these trees somehow. So this, I might need to look at this. Yeah, this shouldn't be -1. It should be minus my size. Oh, this, yeah. So static int just me size, true me equals null, return 0, otherwise return me dot n1s plus 1. Just me size. If it's greater than or equal, okay, so if the size of this kid is less than or greater than or equal to the number on the left, and split there. Yeah, okay, so this might return the wrong answer now, but that's fine. So now n in left equals max.max, n in left and 0. Okay, cool. So let's do this recalculate math. How much time do we have? We got 40 minutes. We should be fine. So how do we do this recalculate method? So there are a couple things we need to maintain these. Okay, so my number of ones is just a constant. My final value is also just a constant. All we need to maintain is the number of ways of doing me and this subtree. And also the subtree size. So the subtree size we can maintain easily. Yeah, the number of ways is a bit tricky. So me dot n ways is equal to either go with ones, me dot n ones minus 1. This is if we use a 10 times ways to make at 10 times 10 plus me dot final value. So we can do that. This should be a multiply. This is like 16. Okay. And then add without ways. So what else can we do? We can do all of the ones, and then we can just have the final value on its own. So like this. Okay, now for each kid, if it's not equal to null, me dot n ways equals multiply me dot n ways with this kid dot n ways. I think that's it. Good. Now let's build the tree. So much fun. Okay. For I can zero as SCP 1 ones. So we'll just I just call this so that it's not deep recursion. That should, it tends to make things faster. It's like doing it iterative, but not really. Let's just make sure this doesn't crash yet. And pre-comp, good. Just one test case even. Very nice. So now we're gonna need a bunch of nodes initially for this entire array. So initially everything starts as zeros. So int array values, just new int, how many digits? N. Digits. Yeah, okay. So we have a bunch of values now. Original one. So now we have to set each thing to this index. Okay, so static void set and index 2. So set index I to original line at I minus 0. Good. And digits. Now what do we do after each query? After it is applied. Yeah, okay. So now for int, or we also need the number of queries. So now set the index to the new value, and now sys out the full tree dot and ways. Yeah, that's it. Okay, so now we just need the set method, which is the entire problem, but it doesn't look like a hard problem now. Okay, so we have to build the tree too. Let's build the tree first. Full treep equals treep dot merge full treep on the left. On the right, we can put a new treep. The number of ones is 0 ones. The initial value can just be a 0. Got it. All right, cool. So now we need to set some index to some value. So we're gonna have to cut that index into pieces first, and then yeah. Okay, so treep array right, or like all both halves is going to be equal to the full treep dot split. How is this going to work? So, we also need this index will be -1. Okay, I think. Yeah. So we have some things. We want to find, we want to cut it there. So the number in left is going to be the index plus 1. So split the full treep. This is just treep.split. How many in the left? Index plus 1, please, and then that will round up. So now we have like the right half and then the left half. So now treep or treep on right equals both halves at 1. So now we want the left half. So treep on left equals treep array left parts will be equal to treep.split both halves at 0. How many do we want in left? We now want both halves, or we want treep.size both halves at 0. That size -1. We want everything but 1 on the left. Then we want that one thing to be on the right. Treep on left equals left parts 0. So now we have the right half we don't care about, the left half we don't care about. And now we need to do some interesting stuff. This is a bit tricky, I guess. So the first thing we need to do is, if this is multiple pieces, we need to cut it in half. Would this be easier if we can just, yeah, we probably want okay, so we probably want a static void merge with thing. Long name. Okay, so we do this stuff. So the full treep is going to be on left, or treep.merge on left, treep, well, okay. So then we'll put it back together again, and we'll be fine. So now we need to do this. We also need to cut it into pieces. So now we have this one part here. So what do we do? Int ones to left is going to be equal to, well, okay, so treat middle because left parts are 1. Okay, so now int ones start with is going to be index minus on left dot size, or size of on left. So that's how many the ones prefix. That this thing has. Ones end width is going to be equal to middle dot size or treat that size middle. So the size of the middle thing minus 1 for the thing that I'm using here minus ones start with. Okay, so now if ones start with is less than 0 or ones end with is less than 0, then I've made a mistake, so I should crash. Okay, so now int first index is going to be equal to merge, yeah, okay, so this is, so now I need to merge stuff back together. So treep middle, or treep to middle equals new treep. The number of ones the ones start with, then what? Then how many ones will I end with? Oh wait, then, okay, so this is, start with a bunch of ones, then your actual value is going to be the value you set it to. Okay, treep new middle right equals ones end with equals 0. If it's equal to 0, then it's just null. If it's not 0, then it's going to be new treep. New treep. The number of zeros will be ones end with minus 1, or the number of ones. Then that ends in a 1. Okay. Full treep equals merge. A bunch of stuff. Okay, so first we want to merge on left with the new middle. Then treep.merge the new middle with the new middle right. Then treep.merge the new middle right with the right. Okay, so now we have to be very careful and combine things that are all ones. Merge with thing on left if it is a 1. So initially, that will be okay. So now this is going to be the on left original size. That'll be the index. And then we do it again where the index is the left plus the middle. Okay, so now I think we just have this method left over. We should finish coding it. Debugging it's going to be the fun part. Okay, so now we have this index, and we want to split it in half, and now the first thing and the last thing might need to be combined. So treat array parts equals full treep dot we'll split full treep into by the index. That's how many parts are on the left. So now we have this left half and the right half possibly. And how do we combine them? So treat array left parts equals parts, well, treat dot split parts at 0. How many need to be in the left? Treat dot size parts at 0 minus 1. Treat array r parts is treat dot split parts at 1. How many need to be in the left? Just 1. So if L parts dot L parts at 1 is not equal to null, and L parts at 1 dot final value is equal to 1, and R parts at 0 not equal to null, then we want to delete L parts at 1. So then R parts at 0 to new treat. How many 1s does it start with? L parts at 0 dot and 1s plus 1 for the one that it has, plus R parts at 0 dot n 1s. This should be a 1 rather. And its initial value is R parts at 0 dot n 1s. Then full treep equals treep dot merge, L parts at 0, treep dot merge, R parts at 0, R parts at 1. Okay. So we've done a bunch of things there, and now we can return. Otherwise, it doesn't actually matter. Like, it isn't actually a problem. So then we can do full treep equals, just sew it all back together, I think. Treep dot merge, L parts at 0, treep dot merge, L parts at 1, treep dot merge, R parts at 0, R parts at 1. Okay. Brilliant. Now, if this works, I will be a very happy man. Doesn't work. Who saw that one coming? much time do we have here? 18 minutes. It's right about what I need, I think. So it's going to be close. Plus there's a non-zero chance this TLE is, oh, it's approaching 0. It's a small chance of TLEs. Very first thing, we set index 0 to a 1. Then we crash. All right, I'm gonna go to the bathroom. I'll be right back. One's start with is less than 0, or one's end with is less than 0. Oh, it's only 2 indices. This should be really easy to debug. Setting the right index 0 to a 1. Okay, index 0 is 1. Okay. So we have just the 2 things. They're both 0. We split this at index plus 1. So we want to cut off the right half. Right size is 1, left size is 0. Okay, one start with index minus, so one start with is 0. One's end with is the size of the middle. Oh. Middle size is 1, that's what we'd expect. So it's 1 minus 1 minus 0. What? How is this less than 0? One start with plus ones. Should definitely be 0 and 0. One start with is -1. index minus the size of on left. What is the index? The index is 0. What? One start with is -1. Index is 0. 0 minus the size of on left, which is 0. How on earth oh, they are 0 and 0 here, but now they're not. Hmm. 0, 1 is... Oh no, 0, 1's fine. That's 10. 10 is a fine number. 10 is a legal number. So first we have the number 10. Well, after this we should have the number 10. First we didn't need to merge, then we did merge. So now we have just one element that's a 10. Got it, okay. So now we set index 1 to be equal to 4. Yeah. So when we split it, we get 0 on the right and 4 on the left. One to start with is negative. Oh darn, I'm doing this wrong. Okay. So I split it at index plus 1. So basically if it's a tie, what if I try and cut something in half? If I try and cut something in half, I want it to go to the left. That's how I've been. Is that what happens? What happens is it goes to the right. Let's make it go to the left if it's a tie. The size of the left kid is bigger than or equal to is bigger. So let's do plus, what did I call this thing? Just me size of me. Yeah. 1512. Oh my goodness. 1512 and a crash. Still quite good though. $15, $12, what was it? So then we set index 1 to be a 0. So what is this? This is 0, 1. This doesn't crash, darn. Okay, so maybe let's try one query. We set 1 to 0. Oh, it's 10, 0 even. That doesn't crash. Okay. So initially this was 11, and now we set index 1 to 0. Okay, that crashes. So we have one prefix with a 1, and that's it. On right size is 2. It should not be 2. I'm running out of time. Just me size is 2. Wait. You cut me in half. Go to the left. The size of your left kid plus the size of me is bigger than the number in the left. Let's redo this all. Size of the right kid is smaller than or equal to int n in right is equal to the size of me minus n in left. Less than number in right, oops, plus just me size. The size of my right kid is smaller than the number in my right. Oh, wait. Yeah, I think that's what I want. That may change the value, I'm not sure. Is this as close to right as I was before? Have I just made the logic way more complicated? Man, out of time. It's unfortunate. So close to. Yeah. Oh well. Big part of that was because I spent so much time on D that I didn't need to. Better luck next time. Yeah, okay. Let's review problems quickly. So, how do we do them? I don't know. To be honest, I'd be pretty surprised if that was still rated, but whatever Mike says, right? Okay, so problem A. Problem A, you've got a permutation, you want to find like some peak in it. So you have a bunch of elements in your permutation, and maybe they go like this. And what you can do is you can store your first element, and then as long as like this first prefix decreases, then you want this to be your first element. So you've got your first element here. As long as it goes down, this keeps being your first element. You can use some exchange argument, because if it goes down, then you want to find the first thing bigger than it, right? So if you later on see an element like this, then that would be helpful. Because like this one would be a better start than this, because this could be a second element for this lower start, but not for the bigger start. So as long as it goes down, you set your first element to be this. Then once it goes up for the first time, then you set your second element to be this. So now you look at however much it goes up, and as long as it keeps going up, you keep replacing your second element with the new increase. And eventually it'll go down again, and then this will be your third element. So then one answer would be this here, this here, and this here. You can just keep switching your pointers as long as it's beneficial to do so, and then you have your answer. So that's problem A. You'll definitely find it if there is. You'll definitely find it with that method if there is some peak. Very good. Let's look at problem B, universal solution. So I guess the problem name kind of hints at what the answer is. But the idea is that if you have some random string of rock, paper, and scissors, if you're going to pick a random starting point and shuffle it by a random amount, then each one of their choices will have an equal effect on all of your choices. Which means basically all of your choices, like the position of your choices doesn't matter at all. There's no significance to it. So there's no reason for your choices to be different in any two positions, because them being in different positions in the array doesn't actually change anything. So if a rock is better in this position, then it's also going to be better in every other position, which means the array you pick is literally just going to be all of the same value. Yeah, very good. So you just figure out what would win most often of all of the things you could pick. Here's the code for that. It's pretty easy. You just see how many things of each of theirs are there, and then figure out what is most common, what would win most, and then print that for the answer. Awesome, that is problem B. Oh, can we see the problems? Okay, I'll have to look at my solutions to figure out what the problems are then. Problem C. Oh yeah, this is the one with the groups. So you have a bunch of groups and you want to know, like you have a bunch of people. Maybe it's like 2, 5, 7, 9, 11. I think these are the groups. And then you want to make groups where the minimum in each group times the number of things in that group is bigger than equal to k. So we're given some integer k. What we can do is we can notice that if you have your groups, you're going to want those groups of people to be continuous ranges in this sorted array. There's no reason not to do that. But it's possible that you might have someone who's really bad that hurts the whole group. And like this 2, for instance, is just such an unhelpful being that it's better to just get rid of them entirely. And now this group has a higher total. So before it had a 3 times 2, now it has a 5, or a 3 times 3, now it has a 5 times 2. So now it's made better. The other thing is, if we have some group that's valid, there's no reason to extend it to make it longer. If it's already valid, then we might as well just use it as it is now. So what we could do is we can like do a greedy from the biggest to smallest, and we can say, okay, let's look at this 11 group first. This 11 group is valid, so let's just use it by itself. And then we want this 9 in the next group, so we'll use this 9, but a 9 by itself is not bigger than the k equals 10. So we need to include other stuff. So now the best we could possibly do is include this 9 and this 7. And now all of a sudden this is valid, so we might as well just use this as well. Now we have this 5 group, and we try and include the 5 and the 2, and that gets too small, so it doesn't actually work. So that's my solution. It's greedy. It's pretty straightforward, pretty easy to implement. I guess you got to be a little careful with where things are, but it's not too bad. All right, can we see problem D? There we can. Problem D, Berserk and Fireball. So this, ooh, man, this is a sob story for me. I had it 40 minutes in. I didn't actually solve it for ages. But anyway, it's a pretty easy problem, as long as you don't mess up like I did. And the idea is that you have a bunch of indices, or a bunch of people. So maybe your people have powers like 4, 7, 3, 2, 5, 1, and 8. 1, 2, 3, 4, 5. Oh, we need a 6. Maybe a 6 there. 1, 2, 3, 4, 5, 6, 7, 8. Cool. So it's going to be a permutation initially. And then there are also a bunch of people that you want to end up like staying alive. So maybe this 7 stays alive, this 5 stays alive, and the 1 stays alive. And everybody else you have to kill. There are two ways you can kill someone. You can pick two adjacent elements and you can kill the smaller of them, and that has some cost. Or alternatively, you can pick some range of length k and shoot a fireball at that range, so maybe k equals 2 in this example, and we could kill both of these people with that fireball. Fireball has some other cost. So what we can notice is these people that we're going to keep alive, since we only ever kill consecutive ranges of people, then we can't ever have a fireball that crosses these people. They are just going to have to live. So we eventually just have a bunch of independent subproblems. So here's one subproblem, kill the 3 and the 2 without killing the 7 and 5 for the minimal cost possible. We also have this problem, kill the 4 using the 7 and nothing is over here, so you can imagine a -1 for the minimal cost possible. Then we have this subproblem. We also have this subproblem. So we have a bunch of different subproblems. We want to solve all of them. We want to do each one for the minimal cost. If any one is impossible, the whole thing's going to be impossible. And yeah, so how do you do it? So if you have some endpoint here, maybe we have this 7 and this 5, and we want to keep both of those alive, and we want to kill this 3 and this 2. We can brute force the number of people that we're going to kill using the berserk, so the number of pairs we pick and kill the smaller one. And then if after that, after we kill all these people with berserk, we have to kill the rest with fireball. So that means the number left over, mod the fireball range, is going to have to be 0. So if the fireball range is 2, we could kill 0 people, or we could kill both people, and then not use a fireball at all. Now, the thing we have to be careful with is that if we want to kill everybody in the range, that means in the last step, we have to use berserk with one of these people. And the person who's going to be left is going to be the biggest one in the range. So if we want to kill everyone in the range with berserk, then we have to make sure that the bigger of our two endpoints is bigger than the max in the range. Otherwise, it's impossible. And yeah, I think that's it. So you just brute force, you've got the two ranges here, and then you brute force how many you're going to use. You have this one case where you might not be able to do it. In other cases, it's just the number of berserks times the berserk cost plus the number of fireballs times the fireball cost. All right, very good. So that's problem D. Let's talk about problem E really quickly. So in problem E, what was this? Oh yeah, you have the towers. So this one's pretty self-explanatory, I think, if you look at it for a minute. So if you've got 1, 2, 3, 4, 5, and 6, these are your two towers. Then what you're going to have to do is you're going to have to cut this tower here between the 1 and the 4 in order to put the 1 over here. Then you're going to have to cut this tower here between the 3 and the 4, and then you'll have to cut, well, then that's it, right? So you have to lift up the 1, lift up the 3, and then lift up the 4, I guess. Yeah, like that. So what we can notice is basically you can combine the 2 and the 3 because they are adjacent values and they're next to each other. So we just want to count how many times are there two adjacent values, how many times is there a value where the value below it isn't what should be below it. So in this case, there are 3, and I'm going to call that the potential. That's the number of moves it takes in order to sort these two towers. And that's true with these towers. It's also true if this one, instead of being this tower, was over here. Right, so it doesn't matter how many towers you use. Cool, so now what we can do is in order to merge these two things, we can always merge the smaller tower into the bigger tower whenever we want to merge two towers. And that's pretty easy to do. We just take whichever one's smaller, and then we take this 1 and we put it in this tower here. We just have to maintain, was this right above something else? And if it was, when we move the 1 over, we have to add 1 to our total. So then we move the 1 over here. And now let's say we had a 2 over here as well. So let's say we had this 1, 2, right? So we have 1, 2, and there's a split point here. So when we move the 1 over, then we create an extra split point. When we move the 2 over, we delete the split point that was below the 2 and also the split point that was below the 1. So we delete 2 split points. So we just have to keep track of that. You can do that using sets in C++. So your runtime is going to be n times log squared. Yeah, and that's it. So the reason it's log squared is because the maximum number of times one element can get moved from one set to some other set will be log n, because the size of its set will double each time you move it. So that makes the runtime n log squared. You can also use hash sets into like arrays is what I had to do in order to get it to run fast enough. All right, last problem really quick because I've got like 2 more minutes here. The strange addition. So the strange addition, what you can notice, there are a couple observations, but the first thing is you could do a DP naively, and that would be n squared runtime, which would be the right answer, but too slow. So instead, what you can notice is if you add 2 numbers, like if you have this a plus b, and these are a and b are both 1-digit numbers, then you know that this number is either going to be less than 20, so it's going to like start with a 1, and then be maybe some other number, or it's going to be a single digit. If it's a single digit, it's really easy for us to calculate the answer. If it starts with a 1, that limits the number of cases. Like there aren't that many, like if we have like some string of digits, right, we want to see how we're going to split it up. Then this group we don't know, but we know this has to be the start of a new group. So we know this 2 has to be on a group by itself. And then these also have to be a group by itself. This has to be its own group, and this has to be its own group. If we have each of these groups, we can use a DP, because we can do a DP for just the ones. If you have a string of ones, how many ways are there to do that? So we can do a DP for each of these groups. And we can maintain what these groups are using a treep. So I won't go into all the details with that, because it would be kind of long. But you can maintain what these groups are with a treep, and then you can also maintain the number of ways to do each group with a treep. And then the total number of ways to do the entire string will just be the product of each of the elements in the treep. And you can maintain that as a range aggregate. So I didn't finish implementing it. Like one thing that's kind of tricky is if you change this 2 to a 1, then you have to combine these 2 ranges. And then if you change like this 1 to a 4, then you have to split the 2 ranges up. So it shouldn't be that hard to do. I just had issues implementing it. All right, so hope you enjoyed the set. Hope your rating went up if it was rated for you. That's all for today. So yeah, I hope you enjoyed. Goodbye.